We're recording now. We're going to start with some math problems, and then we're going to move into some more concept kinds of things. So first thing we're going to talk about is the unit of radioactivity and converting becquerels and curies. Know that a becquerel by definition is 1 disintegration per second. The conversion between millicuries and megabecquerel is 1 millicurie is 37 megabecquerel. So make sure you know those two things. And then we need to be able to make our units bigger or smaller. And the unit here can be anything. I don't know why that keeps happening on my screen. The unit can be anything. It could be meter, liter, it could be grams, it could be becquerels, it could be curies. And if you memorize the order of these, they're all separated by 1,000. Okay. And so if you know the order, then you can do conversions to make the units bigger or make the units smaller. So we're going to do a couple of those problems. We're going to convert 10 millicuries to microcuries. So we're going to go from milli to micro. They're right next to each other. I'm always going to start with what I'm given. And whenever I do a conversion, the very first thing I do is whatever's on top goes on bottom. Milli and micro are right next to each other, so I can do this in one step. Whichever unit is lower in the list, that's the unit that gets the 1,000. The micro is lower, so I'm going to put 1,000 next to the micro. And millicurie cancels. I'm left with micro. 10 times 1,000 is 10,000 microcuries. Now let's do two steps. Let's go from the unit of the curie to the milli and then to the micro. 1.3 curies to microcuries. So I start with what I'm giving of 1.3 curies. Whatever's on top goes on bottom. From the unit, I can go to milli. Whatever's lowest in the list, the milli is lower. That gets the 1,000. Curies cancel. From milli, I can go to micro. So again, whatever is on top goes on bottom. Put micro on top. Micro is lower in the list. It gets 1,000. Millicurie cancels. I'm left with microcuries, which is what I want. When you multiply this, you get 1,300,000 microcuries. Now we can do the same thing on the top, going from megabecquerels to giga. So I'm going to go from mega to giga. 5 times 10 to the second is equivalent to 500. 500 megabecquerels. First step, whatever's on top goes on bottom. Mega is right next to giga, so I can put giga on the top. Whatever's lower gets the 1,000. This time the mega is smaller, so the 1,000 goes on the bottom. Mega cancels. I'm left with giga. My answer is 0.5 gigabecquerels. Now, to convert between units, I can go from millicuries to megabecquerels. So I'm going to start with 25 millicuries. Conversions, again, are just like doorways. Whatever's on top is going to go on the bottom. I'm going to put megabecquerels on the top, and then I'm just going to write in my numbers. 1 millicurie is 37 megabecquerel. Millicuries cancel, and I end up with 925 megabecquerel. Now I can also convert between units and then make the unit bigger. So I'm going to go from 120 millicuries to gigabecquerels. So I'll start with 120 millicuries. I'm going to use my doorway. 1 millicurie is 37 megabecquerels. Millicuries cancel. I'm not done because I'm at megabecquerels and I have to get to giga. Whatever's on top goes on bottom. Mega and giga are right next to each other. Mega is smaller, so it gets the 1,000. Mega cancels. I'm left with giga. I take 120 times 37 divided by 1,000. I end up with 4.44 gigabecquerels. Okay, are you following me? Good. Mm-hmm. Let's keep going. Now we're going to go from 2 millicuries to disintegrations per second. And I know by definition, a disintegration per second is a becquerel. So I know I have to get to becquerels in order to get to disintegrations per second. So I'm going to start with the 2 millicuries. Whatever is on top goes on bottom. Use this doorway first. 1 millicurie is 37 megabecquerel. Millicuries cancel. I'm at megabecquerel, but I know I have to get to becquerel. So I'm going to put megabecquerel down here, kilobecquerel here. Kilo is smaller than mega, so kilo gets 1,000. Megabecquerel cancels. Whatever is on top goes on bottom. Put becquerel here. The becquerel is smaller than the kilobecquerel, so the becquerel gets the 1,000. Kilobecquerel cancels. And by definition, 1 becquerel is 1 DPS, so I can just mark out becquerel and put in DPS. I'm going to say 2 times 37 times 1,000 times 1,000. It's going to give me 7.4 times 10 to the 7th disintegrations per second. One more, and then we're going to move on to something else. Now we're going to count a sample for 1 minute, and we get 320,000 disintegrations. So that's 320,000 disintegrations per minute. And I want to know how many microcuries are there. So first I have to get to becquerels, which is a disintegration per second. This is where most of the mistakes are made, right here. Whatever's on top goes on bottom, DPS on top. The conversion between DPS and DPM, I want you to think dollars per second and dollars per minute. If I give you $1 per second, you get $60 per minute. That's your conversion. That cancels. DPS by definition is a becquerel. Now I'm at becquerels. I know in order to get to curies, I need to get to megabecquerel first, because that's my doorway. I'm at becquerel. So I'm going to go from becquerel to kilobecquerel. Becquerel is smaller. It gets the 1,000. That cancels. And then from kilobecquerel, I can go to megabecquerel. 1,000 kilobecquerel is 1 megabecquerel. That cancels. Now I can use my doorway because I'm at megabecquerel. 1 millicurie is 37 megabecquerels. Almost there. I have to get to micro. I'm at milli. So converting up and down is when we use the 1,000. So I'm going to put millicuries down here, microcuries up here. The micro is smaller than the milli, so it gets the 1,000. Millicuries cancel. I'm left with microcuries. All I do is multiply across the top, divide across the bottom, and in your calculator. And later I want you to go back and do all these calculations and make sure you get the right answer. You should end up with 0.14 microcuries. That's the unit of activity. The next unit we're going to talk about is the unit of exposure. Unit of exposure is literally ionizations in air. This is the unit that we use for all of our gas-filled detectors. GM meter, the portable ionization chamber, and the dose calibrator. Even though the dose calibrator converts that to activity, it's actually reading these ionizations in air. The unit is the Rankine. The SI unit is the Coulomb per kilogram. And so we'll need to be able to convert those back and forth, and we'll have some practice problems in a minute. So the Rankine is used for gamma rays. Particles can still cause those ionizations, but it's measured, it's calibrated for gamma rays. And these things aren't really important because we are going to use everything we use is under 3 MeV anyways. The second unit is the absorbed dose. Now, this is the unit we use when we're talking about how much radiation we gave to the patient, how much radiation was absorbed in the patient's body. The traditional unit is the rad, the SI unit is the gray. And so this conversion is easy to remember because there's 3 numbers in 100 and there's 3 letters in rad. So the 100 goes with the rad. And that's going to be the same when we get to REMS and sievert. There's 3 numbers in 100. There's 3 letters in REM. All right. So we'll skip that. The equivalent dose, this is the unit that equivalates for the type of radiation. So we know not all radiation is the same. X-rays, gamma rays, electrons, and positrons have a radiation weighting factor of 1, which means that the absorbed dose is the same as the equivalent dose. But when we talk about these higher particles that have charge and have mass, they have a higher radiation weighting factor, which means they do more damage. So you take the absorbed dose, the rad, times the radiation weighting factor and gives you REM. You take the gray, which is the absorbed dose, you times it by the radiation weighting factor, and it gives you sievert. So you have to stay in traditional units or SI units when converting from absorbed dose to equivalent dose. So let's go ahead and do this problem. We have a researcher that accidentally ingested a mixture of chemicals and had a dose to the liver of 50 milligray, which is 5 rads, from alpha particles, 30 milligray or 3 rad of beta particles, and 20 milligray or 2 rad of gamma rays. And the radiation weighting factor for alpha is 20. For beta and gamma, it's 1. So the first question is, what is the absorbed dose? And then we want to know what is the equivalent dose. Absorbed dose is in rad and gray. Equivalent dose is in rem and sievert. So for the absorbed dose, it's already in rads and gray. And so all I have to do is add them. 50 milligray plus 30 milligray plus 20 milligray is 100 milligray. 5 rads plus 3 rads plus 2 rads is 10 rads. That one's done. Now to get to equivalent dose, I have to multiply by the radiation weighting factor. So I'm going to start with my SI units. I'm going to say 50 milligray, and that was alpha. Alpha has a radiation weighting factor of 20, so that gives me 1,000 millisieverts. My unit changes when I multiply by the radiation weighting factor. 30 milligrays, radiation weighting factor for beta is 1. It turns into 30 millisieverts. And the same thing for gamma, 20 milligray. Gamma has a radiation weighting factor of 1, 20 millisieverts. Now I have to do my traditional units too. 5 rads of alpha. I'm going to multiply that by 20. Gives me 100. Rad changes to rem. 3 rads of beta times 1, 3 rem. And 2 rad of gamma times 1 again, 2 rem. So absorbed dose times the radiation weighting factor is equivalent dose. Rad times radiation weighting factor is rem. Gray times radiation weighting factor is sievert. All right, last one that we're going to talk about is effective dose. Now we're going to take into consideration the where in the patient's body they were exposed. If they were exposed to the whole body, that means every single organ got the same. The weighting factor is actually 1.0. But if they were only exposed to the stomach, it's 0.12, etc. So in my example here, I'm assuming that somebody got 1.7 rads to the lungs from gamma, X-ray, or electrons. This is absorbed dose. So I have to go from absorbed dose to equivalent dose to effective dose. So I start with my absorbed dose, 1.7 rads. To get from absorbed dose to equivalent, I multiply by the radiation weighting factor. So this is 1. Turns into 1.7 rem, which is what we just did. Now the last step is, it was only to the lungs. I find lungs, it's 12. Take my 1.7 rem times 0.12, and it gives me 0.204. And here's the tricky part. Unit is still rem, but we put on a qualifier. We say it's effective dose. All right, let's skip that one and let's do this one. Actually, I'm going to give you the answer to this one so you can go back and solve it later. The answer comes out to be 3 rem or 0.03 sievert. All right, let's do this one together. Calculate the effective dose. We have 2 rads of alpha to the bone marrow. Weighting factor for bone marrow is 0.12, and 100 millirad of gamma to the bone surface. Weighting factor for bone surface is 0.01. So I start with my 2 rad, recognizing that that is in the unit of absorbed dose, and I need to go from absorbed dose to equivalent dose. So I'm going to multiply by the weighting factor. Alpha is 20. It gives me 40. My unit changes from rad to rem. Now I'm going to multiply it by the tissue weighting factor. 40 times 0.12 equals 4.8 rem, still rem, but now I put on the qualifier and say it's at the effective dose. All right, the second one, 100 millirad. Again, I recognize I'm in absorbed dose, so I have to go from absorbed dose to equivalent dose by multiplying by the radiation weighting factor. For gamma, it's 1. Now my unit changes from millirad to millirem. I'm going to multiply that by the weighting factor for the bone surface, 0.01. And that's going to give me 1 millirem. And again, I put on the qualifier effective dose. Okay. So effective dose is what is reported on your dosimetry reports. So you wear your radiation badges and you get the effective dose. You get the total effective dose equivalent, TEDE. Now, where that comes from, it comes from the deep dose plus the committed dose. Both of these, the deep dose and the committed dose, are your exposure to your internal organs. So this isn't your extremity dose. This is what you're getting on the inside. The difference is the deep dose comes from sources outside your body. Committed dose comes from sources inside your body. The only way to get a committed dose is if you ingest, inhale, or inject radioactive material. So hopefully you don't get that. Hopefully you just have a deep dose, which will equal your total dose equivalent. Shallow dose, that's your separate badge where you wear your ring badge, or it can also be extrapolated from your whole body badge. And then the lens of the eye dose, that also can be a separate badge that you wear on your eyeglasses, or can be extrapolated from your whole body badge. All right, just make sure that you know all of these limits here. This is the public dose, which is 100 millirem. These are all special members of the public. I like to think of them as special. The fetus, people under the age of 18, and family members of radiation therapy patients, they all get 500 millirem. And then we have to convert between rems and sieverts. So we're going to do a couple more conversions, and then we'll move into some more concept kinds of things. All right, so these are the 3 conversions that you need to know. Conversion problems. Again, conversions are doorways. We're going to start with our 3 Roentgens. First step in a conversion is whatever's on top goes on bottom. This is the conversion I'm going to use. 1 Roentgen is 2.58 times 10 to the negative 4th coulombs per kilogram. Roentgen cancels. Now, you're never going to separate the coulomb from the kilogram, so just think of that as just 1 unit. The unit is coulombs per kilogram. When I multiply that, I end up with 7.74 times 10 to the negative 4th coulombs per kilogram. All right, converting rads to gray. I'm going to start with what I'm giving, 50 millirads. I'm going to show you a little shortcut because I don't have to go all the way to rads and then rads to gray and then back to milligray. I can go straight from millirad to millirad to milligray. So I'm going to put my conversion in here. 100 rad is 1 gray, but this is milli. So I'm going to go ahead and put milli down here and put milli up here. As long as I do the same thing to the top and the bottom, conversion remains true. Millirad cancels. I'm left with 0.5 milligray. Now I can take my 0.5 milligray and convert to microgray. Again, this is making units bigger or smaller. Milligray is going to go on the bottom, microgray on the top. Micro is smaller, so it gets the 1,000. Milligray cancels. It comes out to 500 microgray. And I can do it the other way as well. I'm going to go ahead and give you these answers. This comes out to 80 millirad, and I want you to solve them later. If you have any trouble solving these, let me know via email, and I can help you out, okay? All right, last one, we're going to go from millisieverts to millirem and rem. So I'm going to start with what I'm given, 8.5 millisieverts. I'm going to put in my conversion here, sieverts and rem. 100 rem is 1 sievert, but since this is milli, I'm going to put milli in front of both of these. Milli cancels. I'm left with millirem, which is what I want, 850 millirem. Now I can take my 850 millirem and convert it to rem. Whatever's on top goes on bottom. Put rem on top. Milli is smaller than the unit, so that gets the 1,000. Millirem cancels. I'm left with 0.85 rem. All right, these are all the things we have covered in a very short 20 minutes. So this is a lot. Make sure you know all of these. All right, now let's move into some more physics-y stuff that has to do with the atom itself. Proton and the neutron are found in the nucleus, and the electron is obviously found outside the nucleus. Most of the mass, almost all of the mass, because these are huge compared to how small an electron is, most of that mass is concentrated in the nucleus, and mass can be converted to energy. So we use those terms interchangeably. So that means we have more energy in the nucleus. Gamma rays come from the nucleus, and since there's more energy in the nucleus, gamma rays tend to have more energy. not always. Electrons have less mass, so they have less energy. X-rays come from the electron cloud, which, by the way, that's why we're called nuclear medicine, is because all gamma rays come from the nucleus and X-rays come from the electron cloud. Now, nuclide nomenclature. In order to understand this, we need to understand mass numbers and atomic numbers. The mass number A, you can think of A as standing for all. It's everything that's in the nucleus. It's protons plus neutrons. It's all. Z is just the protons. Okay. We could also put an N here, and that's the number of neutrons. So if we did that, this is what our nuclide would look like, and that's very busy. Well, we don't need that 78 because we can calculate that 131 minus 53. So we could write it like this, but we don't need the 53 because iodine always has 53 protons. So this is the correct way of writing it. That is the mass number. That is the total number of protons and neutrons. Or we can write it like this. Now, families of nuclides. This refers to how nuclides are related to each other. So families mean more than one. We have isotopes, same number of protons, which means they're the same element. So, for example, gallium-67 and gallium-68. Those are isotopes because they're the same element. I-123, I-131, those are isotopes. Isotones are useless. They're basically just the same number of neutrons. Isobars is the important one. That's the same number. So germanium-68 and gallium-68. Those are isobars because they have the same number. Moly-99 and Tec-99m, same number. If they have the same number, they're isobars. And then isomers, that's where you have the same everything, the same number of protons, so it's the same element, the same mass number. The only difference is one has an M because it has a little bit more energy. So very quickly, you can look at these and you say, oh, same letter, they're isotopes. This one, same number, they're isobars. This one's the difficult one. You have to do a little bit of math. You have to subtract 53 from 131, 52 from 130, 78 neutrons makes them isotones. All right, questions on that? Okay. All right, so now let's look at the nuclear line of stability. So if I take all the possible configurations of protons and neutrons, and I plot the number of neutrons on the x-axis and the number of protons on the y-axis, where the number of protons equal the number of neutrons is this line here. That's not the line of stability. The line of stability is the purple ones. All the other ones are radioactive. So the ones that are radioactive are going to be above the line of stability or below the line of stability. If they're below the line of stability, we say they're neutron rich. If they're above the line of stability, we say they're proton rich. If we have too many neutrons, a neutron turns into a proton. And if we have too many protons, a proton turns into a neutron. Now I need to balance these two sides out. Right now, this side is neutral and this side is positive. The only way to make this side positive is to add something negative, which is a beta negative. Up here, this side's positive and this side's neutral. The only way to make these equal, I need to add something positive. I add a beta positive. So below the line of stability, neutron rich decays by beta negative. Above the line of stability, proton rich decays by beta positive. One other one is electron capture. If I have too many protons, I can add an electron. And notice a positive and a negative equals a neutral. That's electron capture. And just to take it one step further, these nuclides are made in a reactor, and these nuclides are made in a cyclotron. All right, so let's get into how they decay and the decay schemes. So when we talk about radioactive decay, we're talking about the parent, which is unstable, and the daughter, which we're going to say is more stable, because the daughter is not always stable. Sometimes it goes through multiple pathways. And the decay scheme itself, think of it as a graph. On the x-axis is the number of protons, and the y-axis is the energy. And there's three possible things that can happen. You can have an arrow going this way, you can have an arrow going this way, or you can have an arrow going this way. The arrow is always going down because the parent is going to lose energy when it becomes the daughter. And the amount of energy that's lost is called the Q value. If the arrow goes down to the right, that means we're adding a proton. If it goes down to the left, it means we're subtracting a proton. If it goes down in the middle, that means the number of protons are staying the same. So let's take a look at these. Beta minus. Beta minus decay, we already said it's a neutron, turns into a proton plus a beta minus. So if a neutron is turning into a proton, that means I've added a proton, Z plus 1. Arrow goes down to the right. Beta positive, now we have a proton that's turning into a neutron plus a beta positive. So if a proton turned into a neutron, that means I lost a proton. And then the last one is electron capture, which of course is a proton plus an electron turns into a neutron. And again, it's the exact same thing as what happens with beta positive. Ultimately, a proton is turning into a neutron. And so if a proton turned into a neutron, arrow goes this way, Z minus 1. Alpha decay, an alpha particle is 2 protons and 2 neutrons. And so if I'm losing 2 protons, the arrow is still going downward to the left, but it's 2 protons that are lost. And then, of course, the last one is isomeric transition, which is like technetium 99M turning to technetium. Arrow goes straight down because it's not gaining protons, it's not losing protons, it's staying the same. All right, so alpha decay is just a helium nucleus that's being given off. Beta minus decay, neutron turns into a proton plus an electron. Beta positive, proton turns into a neutron plus a beta positive. These two are exactly the same thing. They're both electrons, just one's positive and one's negative. Electron capture, you've got a proton plus an electron turns into a neutron. And then gamma emission, you have a little extra energy in this one. When it gives it off, it goes to a ground state. Okay, we're going to skip that. All right, so let's kind of work through some of these and see what happens with the actual numbers. You have a parent nucleus of radium-223. This is the only approved alpha emitter. It's the only alpha emitter that will be on your board exam. It decays by giving off a helium particle, and it turns into radium-219. Let me just check. Okay, yeah. We can also write it like this. A goes down by 4, Z goes down by 2, because that's what an alpha particle is. And we just talked about writing it like this. So, radium-223. Radium-223 has 88 protons. If it decays by alpha emission, this is what happens. 223 becomes 219. 88 becomes 86. If I look that up in the periodic table, it's radon plus an alpha. One other example, plutonium-239. It has 94 protons. 239 becomes 235. 94 becomes 92. That's what's happening. That becomes uranium plus an alpha. All right, now isobaric decay. Isobars, by definition, mean that they have the same mass number. So in each of these, either a proton's going to turn into a neutron or a neutron's going to turn into a proton. Beta minus, a neutron turns into a proton. Beta positive, a proton turns into a neutron. And electron capture, a proton also turns into a neutron. This one is also beta negative. This one's beta positive. This one's plus an electron. Make sure this is just a really important slide. So I want you to concentrate and make sure that you know this, okay? All right, so beta minus. Here's our parent, potassium-40. It's going to decay by beta negative and become calcium-40. And notice this number is always going to stay the same in beta minus, beta positive, and electron capture because they're isobars. We can also write it like this because what's happening is we've got a neutron that's turning into a proton plus a beta negative. It means I'm adding a proton. Right there it is. But this number, which is A, stays the same. And we already talked about that. So if I have P32, has 15 protons, 32 is going to stay the same because it's beta negative, isobaric transition. 15 is going to go up by 1 and become 16. If I look up 16 in the periodic table, it's sulfur. Strontium 89, beta negative emitter. 89 stays the same. 38, I'm gaining a proton, so it becomes 39. Now, beta positive is the crazy one, okay? So beta positive is going to continue to do things after it leaves the nucleus. Beta negative is going to leave the nucleus, and it's going to do what it's going to do. And once it runs out of energy, it's just an electron. And we have free electrons everywhere in the environment, in our bodies, and that's fine. But we don't have free positrons because positrons don't exist in nature. Once the positron runs out of energy, okay, then it's going to connect with an electron, because one of those free electrons that are just out there, and an annihilation reaction occurs. When that happens, energy and mass are interchangeable. So the mass turns into energy, and the energy it turns into is two 511 keV photons that are then picked up on opposite detectors. So this is what it looks like. We have Z minus 1 because a proton is turning into a neutron plus a beta positive. So if a proton turns into a neutron, I've lost a proton. And we already talked about this. Okay, so here's what this looks like. We have carbon 11 with 6 protons. It's going to decay by positron emission. 11 stays the same. 6 is going to go down by 1 because the arrow is going to the left, down by 1 because a proton's turning into a neutron. F18, the same thing. 18 is going to stay the same. The 9 is going to go down by 1, become 8. If you looked up 8 in the periodic table, oxygen would be next to it, Z minus 1. All right, we doing good? Okay? Mm-hmm. All right. All right, so the next one is electron capture. Electron capture is sometimes referred to as the alternate decay pathway to positron emission. And the reason is both are made in a cyclotron. Both of them have too many protons, and both of them, a proton is going to turn into a neutron. But the difference between electron capture and positron emission is positron emission does that spontaneously. Electron capture doesn't have enough energy. And so again, we use energy and mass interchangeably because of Einstein's equation. If I need more energy, I can pull in mass to do that. So I'm going to pull in the mass of an electron. This electron here is going to pull into the nucleus. And when that happens, those two come together and form a neutron. So I'm losing a proton. And then, of course, what ultimately happens after that is I have a vacancy here. This electron is going to fall into its place. And when it does, it gives off an X-ray. This X-ray is called a characteristic X-ray. Then we have this vacancy, and this one falls into its place, and we have a second characteristic X-ray. So I always ask students, like, okay, with electron capture, where's the radiation coming from that we're imaging? Because we can't image particles, we have to image photons. And it actually comes from 2 places. First, this characteristic X-ray, okay? But the second place is that in this nucleus, when this reaction happens, sometimes there's energy left over and it gives it off in the form of a gamma ray. Okay, so 2 different places you get the energy from electron capture. All right, here's what it looks like. Z minus 1, because again, proton plus an electron turns into a neutron, so I've lost a proton. Z minus 1. All right, now I'm going to ask you, tell me what happens here. I-123, what happens to the 123?
Stay the same.
Very good. What happens to the 53?
Minus 1.
Excellent, you got it. All right, same thing here with thallium. Thallium turns into mercury with 80 protons. 201 stays the same. All right, gamma emission. Gamma rays always come from the nucleus. And so that's why we're called nuclear medicine. Gamma emission, these tracers, when we get into radionuclide production, we're going to find that these radionuclides are made from the decay process of another radionuclide, that was made in either a reactor or a cyclotron. So we have internal conversion and we have gamma emission. They're almost exactly the same thing. Gamma emission is just that. A gamma ray leaves the nucleus and it leaves the atom altogether. This goes out and does its own thing. Internal conversion, this is when the gamma ray on its way out, it hits one of its own electrons and knocks an electron out. Okay, and so you can think of it as it's internally converting its own energy to itself. Now that electron is called a conversion electron. There's a lot of different types of electrons. We've got a Compton electron, we've got a photoelectron, we've got a recoil electron, we've got a conversion electron. They're just electrons. They just are made in different ways. So a conversion electron comes from internal conversion, which comes from a gamma ray out of the nucleus that hits one of its electrons on the way out. All right, the last thing we're going to cover is interaction with matter. What happens when these radiations go out and interact with the world? So what matter are we talking about? We're talking about patients, we're talking about cameras, talking about other radiation detection instruments, talking about ourselves. What happens? Now, particulate radiation is going to interact differently than photons. So particulate radiation is alpha and beta, beta minus and beta positive, and it's going to react differently because it has a charge, it has mass. Because it has a charge, it's either going to attract or repel electrons. So the alpha particle has a +2 charge, beta positive is +1, beta minus is -1. And so as it attracts or repels electrons, it removes them, which is the definition of ionization. Ionization is the removal of an electron. So let's talk about alpha first. So alpha, you have the unstable parent, you have the more stable daughter. Alpha particle is emitted, has very high charge, high mass, and because of that, it doesn't go very far. So we do not use that in diagnostic nuclear medicine. At rest, it's a helium nucleus, not a helium atom, because it does not have any electrons. If it had electrons, it would be a helium atom. 2 protons, 2 neutrons. Here's what it does. Here's the alpha particle compared to the electron. All of the dots are ionization events. So you can see that the alpha particle has a whole lot more ionization events than the low linear energy transfer of the electron. So when it interacts, it's going to produce a lot of damage, whereas the electron doesn't produce as much. The other thing I want to point out is alpha particles travel in a straight line, beta particles travel in an erratic pattern. And this is both beta positive and beta negative. Now with beta negative, we have to be concerned about something called bremsstrahling. Bremsstrahling is when you have your beta negative particle and it's traveling through matter and it comes close to a nucleus. Nucleus is positively charged. Beta negative is negatively charged, so they're attracted to each other. And so it's coming through and it's attracted to this nucleus and it causes it to change directions. Now, whenever you're driving in your car and you have to change directions, you have to hit your brakes and slow down. This is called braking radiation. The excess energy has to go somewhere because in physics, energy is neither gained or lost. It has to go somewhere. And where it goes is it creates this photon called a bremsstrahling photon. This is an X-ray. Now, we talked about characteristic X-rays and bremsstrahling X-rays. Those are the 2 types of X-rays that you're also going to find in an X-ray tube. Okay, and so when we get into instrumentation, we start talking about that. Those are the exact same things. Now, if I'm a beta negative particle and I'm further away from the nucleus, I'm not as attracted, so my curve isn't as steep. It's a wider angle. If I'm further away, I'm going to have a lower energy X-ray. If I'm closer, I'm going to have a higher energy X-ray. And it's equivalent to how much you have to slow down to make that tight curve, or maybe you only have to tap your brakes to make a wide curve. Okay, now beta positive. And this is where I want to spend a little bit of time because I think this is so important. When the beta positive particle leaves the nucleus, okay, so you had a proton that turned into a neutron, plus a beta positive particle. Everything stays in the nucleus except the beta positive. It leaves, but it's going to have a certain amount of energy associated with it. Okay, so there's energy that's left over. Like it's kind of like when you send your kids off to college, you give them a little money so they can pay for things. So the beta positive particle has a little bit of money it needs to spend. It has to spend all of its money before it can annihilate. So it's going to travel a certain distance. It's not going to travel in a straight pattern because beta negative or beta particles don't travel straight. But the amount of energy it has determines how far it goes. Why is that important? Well, this is where the annihilation occurred. This is where the photons are picked up. This is where the camera thinks the tumor is, but the tumor is all the way back here. So this distance introduces error, and it introduces that error in every single direction. Now, how much error are we talking about? It depends on the beta positive particle. Here's all the beta positive particles. F18 has an energy of 633 keV. So in order to run out of its energy, it has to travel 0.3 millimeters. Whereas rubidium-82 has 3.35 MeV, a whole lot more energy. So it's going to travel a longer distance before it runs out of energy. So the higher the energy, the farther it's going to travel. And I would make sure that you know this one, and this one, and this one. Those are the important three. All right, so it's going to travel a certain distance. Once it runs out of energy, then we're going to have this annihilation reaction, which is literally E equals mc squared. The mass is going to turn into energy. So the distance it travels is the first source of error that we cannot accommodate for, okay? It's just going to be an error in every direction. The second source of error is when this annihilation actually occurs. Sometimes there's just a little bit of energy left over in that positron, or sometimes the electron has a little bit of energy, which means that these photons are not going to be exactly 180 degrees apart. We call that non-collinearity. And if they're not exactly 180 degrees apart, the camera is going to pick it up in the wrong location. So that's the second source of error with PET imaging. That's why we're unclear medicine. We'll never be clear. Okay, so that's how the image is all. Go ahead.
Is that meaning that rubidium will have more error than the other, than F18?
Yes.
This is the longest. Okay.
Yes.
But this is the imaging for the heart, so is that meaning it's not as accurate as the F18?
So technically, that's what it means, but clinically, that's not what it means. So technically, that is correct, but clinically, it's not. It doesn't make a difference. The salespeople for flurpiridaz, which is going to be the competitor for rubidium, the salespeople are going to tell you that. They're like, oh, our images are much more accurate. And technically, they're correct. So when they come into your department, they try to sell you that. Tell them, like, technically, you're correct, but clinically, you're not.
Okay. Thank you.
You're welcome. All right. So then all of this, what happens is in the detector, you have all of these lines of response that are going off in opposite directions. And where they intersect, where the intersection is where the annihilation occurred. And that's where the dot goes on the screen. And you have all of these dots that come together to form an actual image. All right, now let's talk about photon interactions. Okay, so photon interactions, there's no charge, there's no mass, there's only energy. And because of that, photons go really, really far. In fact, I-131. Have you ever done an I-131 therapy? Okay, so I-131 is beta negative. That's what does the magic, but it also has a gamma emission. And when we are teaching our patients about radiation safety when they go home, this is what we're concerned about, not this. Because unless you get this inside of you, it's not going to hurt you. But this I-131, it has a high energy and it's going to go really far. And that's what, and it has an 8-day half-life. So they're going to be irradiating patients all day long, or their family members. So long range. Okay. So photons are on the electromagnetic scale, which means there's an electrical field in one axis and a magnetic field in the other. They're all traveling, and as they travel, they're traveling at the speed of light, okay? Speed of light. So The photoelectric or the electromagnetic spectrum, we have gamma rays and X-rays all the way up here because they're high energy. We have radio waves down here. In the middle, we have visible light. And the colors on the scale go from red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Red is down here, so infrared is right below it. Infra means below red. Ultra means above, so it's above violet. So that's how you can remember where those are located. So this is high energy. It has enough energy to cause ionization. So these cause ionizations, which is the removal of an electron. They also are going to have high frequency and a short wavelength. That's how they are related. So what do? There's really three interactions we can talk about. The first one is no interaction at all. That's the easy one. And that's going to happen in us, okay? Because we are low Z material. When I say Z, I'm talking about this right here. How many protons are in the nucleus? So if I have low Z material, I don't have as many electrons because the number of protons equals the number of electrons. So if I have low Z material, then the photon's going to go right through. Whereas our gamma cameras and our radiation detection equipment is not low Z, that's high Z material. And we do that on purpose because we want an interaction, either a photoelectric effect or Compton scattering. Those are the two that you need to know. So photoelectric effect and Compton scattering, they're the same thing in terms of the incoming photon. The photon comes in and it's either going to interact with an inner shell electron or an outer shell electron. Now, what is the difference between these? The inner shell is really close to the nucleus. We know the electron's negative, the nucleus is positive. And because of that, they're attracted to each other. And if it's really close to the nucleus, there's a high attraction. So if this photon comes in and it knocks out this electron, it takes all of its energy to do it, and there's nothing left over. We call that a photoelectric electron. This is absorption, not scatter. Now scatter, it comes in, it hits this electron. This electron's pretty far away, so it's just barely hanging on. So this photon, it kicks out the electron. Now we call it a recoil electron. But there's a lot of energy left over. And so it scatters, comes down here. Now, if this photon happens to make it through the collimator and hits the crystal, we're not going to count it. Why? Because this photon has less energy than the incident photon because it used some of its energy to kick out an electron. Change directions, we don't want to count it anyways because it changed direction, so we don't know where it started from. It's a source of error, but we can get rid of it because in our pulse height analyzer, we're only going to include what's in the window down here is Compton scatter. All right, I got through that in less than an hour, which means that I have time to quiz you. Are you okay if I quiz you?
Okay, go give it a shot.
Okay, I am going to stop presenting and let's see how we do. I'll be nice, I promise, okay? All right, what is the conversion between millicuries and megabecquerels?
1 to 37.
Exactly, very good. All right, how do you convert millicuries to microcuries?
So it's 1,000 less.
Very good, yes. Okay, how about megabecquerels to gigabecquerels?
Mega, so it's it to move the decimal to the left.
Very good, yes, yes. All right. What is the unit of measurement for our GM meters?
GM, CPM.
The GM meters, not the well counter.
GM.
Yeah, when you use your Geiger counter, what's the unit?
VPM. Not sure. Sorry.
It's the milliroentgen per hour, MR per hour.
Oh, okay.
MR. Yes. All right. What is the conversion between Roentgens and coulombs per kilogram?
Rankin and Cool.
It's a hard one.
2.8 times 10 to the minus negative 7.
Fourth.
Oh, 4. Okay.
Negative fourth, yes, yes. All right, what is the unit of absorbed dose?
And silver and ram. Silver. Oh,
That's
gray.
gray and
Ram.
rad. Think of rad as standing for radiation absorbed dose, and know that rad goes with gray. Okay, red, gray, radiation absorbed dose. All right, what is the unit of equivalent dose?
Units is silver. Silver and ram.
Yes, yes. Think of REM as radiation equivalent man. REM and sievert go together. How do I go from absorbed dose to equivalent dose?
To equivalent is times the 1 to 100.
Okay, so if I go from rad to REM or gray to sievert, absorbed dose to equivalent dose, I times it by something.
The weighted factor
Yes, the radiation weighting factor, right? All right, what's the unit for effective dose?
is ram.
Mhm. It's also REM and sievert, but we put a qualifier on the end and we say this is the effective dose. And how do I get from equivalent dose to effective dose?
The total TEDE plus the DDE.
Okay, so that's for the total effective dose equivalent. But if I'm just looking at, here's the equivalent dose, and I want to know what the effective dose is, I multiply by the tissue weighting factor.
Okay.
All right. What is the difference between deep dose equivalent and committed dose equivalent?
Deep dose is the organs, and then the committed is it the times 50? Is the 50 years?
So deep dose and committed dose are both internal organs. Deep dose is your exposure to internal organs from external sources. So the source didn't ever get in your body. The committed dose means you inhaled, ingested, or injected radioactive material into your body. That's a committed dose. And then you add them together for your total. What is the maximum whole body exposure that you're allowed in 1 year?
5 ram.
Very good. What about the lens of the eye?
Lens is 0.15.
Point, it's 15 rem. 15 rem. Yes, 15 rem. What's the public dose? 0.1 rem. 0.1 rem. All right. What is the conversion between rad and gray?
Red and gray. Red is 1 gray to 100 gram.
Very good. Yes. All right. And how are gallium-67 and gallium-68? How are they related?
They are the same isotopes.
They're isotopes. Very good. All right. How about I-123 and I-131?
The isotopes.
Very good. How about germanium-68, or not that? How about strontium-82 and rubidium-82?
They're the same. There will be isobar.
Yes, yes, isobars. Excellent job. All right. You have something that's decaying where a neutron is turning into a proton. Is that beta positive or beta negative?
I'm sorry, repeat that.
A neutron is turning into a proton. Is that beta positive or beta negative?
Sure.
All right. So if a neutron turns into a proton, it's going to emit a beta negative. And if it's made, if that happens, it's made in a reactor, because in a reactor we're adding a neutron. In a cyclotron, we're adding a proton. All right, let's go. Let's see. What is an alpha particle?
Alpha particle is it's very strong, high ET, short wavelength.
Okay, so it doesn't have a wavelength because it's a particle. It doesn't have a wavelength. So particles are not on the electromagnetic spectrum, only photons. So physically, what is an alpha particle? Is it one proton and one neutron?
It's 2 neutrons and 4 protons.
2 neutrons and 2 protons. So it has a mass number of 4. What's the difference between a beta minus particle and a beta positive particle?
One is for positron and one is for gamma.
Yep, and they're both electrons, and they're both, one's positive, one's negative. All right, tell me what happens to a positron when it leaves the nucleus.
Again, annihilation effect.
Okay, what happens before the annihilation?
It will go into strike the nucleus with the positron range.
Exactly, and what determines the positron range?
It depends on the isotope.
Okay, yeah. So which one has a higher range or a longer range, rubidium-82 or F-18? Very good, yes. And so that positron range is a source of error. What's the second source of error that we talked about with positrons?
Collateral, I forgot the name.
Non-collinearity. What does that mean, though?
It means went to different direction.
It means that they're not exactly 180 degrees apart. That angle is not exactly 180. All right, tell me how bremsstrahlung works.
Is a strike to the closest to the nucleus, and it would make a wide turn break and get out.
Exactly, yeah. So that excess energy is given off. Is that a gamma ray or an X-ray?
X-ray.
Very good. All right, so photoelectric effect, is that an inner shell or an outer shell?
It's an outer shell.
And is it absorption or scatter?
Absorption.
All right, what happens with Compton scattering?
Compton scattering is hit the outer shell, and then it got out, have a scatter radiation.
And how does our camera eliminate Compton scatter from the image?
With the septum.
Not the collimator.
Oh.
It's the pulse height analyzer.
Okay. Yes.
Yep. And setting our window. Yep. All right. Great job today. I'm going to stop the recording.